Okay, so yeah, we are late. So sorry about that. Just wanted to thank everyone to join today's workshop for both projects, PRITIA-CLOUD and Adobe.com. And yes, just I'll do a short introduction for the PRITIA-CLOUD project that we will start with. So as you know, the PRITIA-CLOUD project is successfully ending on June 30. I would like to thank everyone and every of the participating institutions for the great job done. The work done to build really interesting solutions, practical solutions to be used in production environments. Well, just to summarize, we will have presentations from the four technical work packages that we have in the project. So we have work package 1, that is the coordination. So that is something that we won't cover in the workshop today. The second work package that was led by TapTap Digital and the title is Arquitectura Cloud optimizada para la ingesta y procesado masivo de datos en servicios de alta demanda. That will be the first one presented. Then we have the work package 3 that was led by Elastic and is entitled Monitorización y predicción de costes en el Cloud Edge Continuum. And finally, was the work package 4 led by NEC with the name Analítica Avanzada con Garantías de Privacidad en Cloud Edge Continuum. And finally, the work package 5, that is the one that was led by UC3M, and it's called Soluciones de Auditoría de la Privacidad y de la Transparencia de los Servicios Cloud en el Cloud Edge Continuum. So basically, we will cover the results and the solution built for each one of these work packages along this webinar. And I think just for starting, something that I want to mention is that I'm just using English because we have some of the attendees of the workshop who don't speak Spanish, but this is not mandatory. So basically, when I give the floor to each one of you, just use the language in which you feel more comfortable to present your results and your slides. And that's it on my side. Again, thank you to all of you for the great work done in the project to bring it to a successful point. And I think I'll be giving a floor to Victor Iniesta from TapTap Digital, so he can just show us what they have built for the work package 2. Victor.
Hello, Ruben. Good morning and thank you. Good morning to everyone. I will proceed to the presentation of our work. Here you should see. Let me know if you can see my screen, because I have just shared it. Okay, yeah. So in this presentation, I'm introducing the optimized cloud architecture for massive data ingestion and processing in high-demand services. This project is under PRITIA-CLOUD, and it has been developed by TapTap Digital. Just a quick introduction to TapTap Digital. That is a digital advertisement company that has been funded since 2010 and is and its main focus is the digital advertisement with presence with office in 10 countries, headquarters in Madrid, and present in plus that 85 markets. The main problem that we are facing and that we want to solve in these presentations is the current growth in all the data that is being produced by internet connected devices, like can be cell phones, people, devices, that is generating a massive amount of data that is continuously growing, and it has been, and they need to be processed by application services. At the moment, this traffic may arrive to the cloud unfiltered, raw, and we have to dedicate additional resources to process all this information. What this causes is that the application services are losing efficiency, since there is not all the traffic is useful to the application service, is adding higher latency in order to process all this traffic, and we are dedicating much more computational resources, since we need all of them to be able to analyze all this and proceed all this traffic. Efforts to put a pre-filtering logic in with the application service as well mainly causes to add an additional overhead, increasing even more latencies and computational problems. The objectives of our solution is to take advantage of the cloud continuum, where we will locate in the cloud edge, near to the data sources and the users that want to either generate or access this information, a filtering service that will allow to classify and filter traffic before reaching the cloud core, where all the core business is located. That way, we will just let pass the traffic that is significant to the application service, reducing the computational service needed to process all this information and improving all latency and performance. Also, by separating this functionality of pre-filtering in the cloud edge and leaving the cloud core for the main business knowledge logic, allow us to manage each one of them differently, adapting and applying resources independently to each one of these different parts of the cloud continuum. We have several real-world examples of this problem. For instance, what involved in the real-time action, like is the stock market or in the programmatic advertisement, when the traffic that arrives represents opportunities of investment, and we have a very small window of opportunity to make a decision if we want to invest or not, just to maximize our investment. Also, we have the example of social network, where we have millions of users that are generating interactions, contact for cultural events, news, or in viral events that may generate a spike on data that we need to process, interpret, and know which is the relevant information that we want the user to be shown or to display in our social network application. Also, we have the Internet of Things, where we have an heterogeneous network of devices, ranging from sensors that measure temperature, humidity, presence, to routers that indicate Wi-Fi availability, and all the range of wearable devices, that all of them continuously generating data from the monitoring that must be collected, processed, and interpreted in order to generate, for instance, real-time alert under certain condition, or allowing the user to access this information and also historical information in real time. So with this problem, we made a study, and for the solution proposed, we found out the following requirement: that must have an efficient real-time traffic filtering. It must collect metrics in order to know the status, both from the business to understand which is the application service needs, and also it needs metrics from the system, from the architecture and its component to know which is the current status and load and times of all the cloud components. We have a second, we need to know the demand, which is the demand by the application service, which kind of traffic or data at a given moment the application service needs in order to provide the expected service or the expected outcome. Also, between among all this traffic, there is a subset of the traffic that will allow us to maximize the expected KPIs or outcome for the application service. For instance, for the stock market, we would like to identify which are the investment opportunities that will maximize the revenue, and we are much more likely to win. And also, in order to adapt to the continuous changes of the traffic and data being received, we need auto-scaling capabilities to be able to adapt dynamically or computational resources to the different condition on traffic and load. So with these requirements, we design a proposal for the architecture for all solutions, where we identify the different subsystems that will make up all the architecture. In this case, we have the data collection and persistence will be the subsystem that will be in charge of collecting all the metrics and data from both for the cloud core architecture and components, and also from the application service. All this information will be used later to feed the rest of the subsystem. We have the prediction and scaling. This subsystem will allow us, with all the information from the application system demand and all the information with the incoming data or traffic that we are receiving, to match them, and in order to select the exact traffic that our application needs at a given moment, and just leave the rest. We have the training and optimization models that will take all the historical data from the received traffic in the application service and how it has been managed by it, and through machine learning procedure, we'll be able to generate machine learning models that will allow us to evaluate how likely incoming traffic will maximize the target KPIs of our application. And we will need to, through the exploitation of optimization model, it will allow us to integrate this model in the main core of our solution, that is the data ingest and processing subsystem that is in charge of receiving all the raw incoming traffic from the different providers, and use the configuration that it has been calculated, all the filtering configuration by the prediction and scaling system, and the evaluation from the training and from the optimization model in order to just to filter and let pass the best traffic, the traffic that will most likely fit the system needs and will maximize the target KPIs. So with this proposal of the architecture design, we have applied to a practical use case that in our case for our company is it focuses in digital advertising. Just an introduction for the advertising ecosystem. We have here in advertising we have two main parties, two main interested parties. Is the publisher, that is the owner of the ad spaces that you may see in your mobile phone, desktop, in digital TV, or on digital screen in exterior. And we have the advertiser, that it may be a company or a brand that has a product or a service that it wants to advertise. So in the programmatic advertisements, the publisher is represented by the supply side platform that manage all the advertisement spaces from different publishers and expose them in order for the monetization. And the demand side platform, the DSP, that represents the advertiser and receive all the ad opportunities and evaluates them against the advertiser campaigns to know which is the best match, and is willing to pay to place their advertisement in that space. So at the moment, advertisement generate millions of opportunities all around the world in a second. And in order to have an scalable advertising communication, the main parties of the advertisement ecosystem define a communication protocol, the Open Real-Time Bidding Protocol, that allows an scalable and efficient communication between the supply side and the demand side. That allowed real-time communications because there is a very tight timing here where the communication between the supply side platform and demand side platform is supposed to happen in less than 150 milliseconds. Here we can see an example of the communication. We have on the left side the publisher that generates a new opportunity for an ad. It has a free ad space. This is exposed through the SSP or ad exchange to the interested DSP as an opportunity through a message called bid request that has all the description of the available space, the device where it's happening, and any other information that is useful for the DSP to match the most suitable campaigns. The DSP evaluate this information, and the ones that are willing to place their advertisement there respond with a bid response, answer back. The DSP receive all of them. This communication until here, it has happened in less than 150 milliseconds to be a valid bid response. With all this valid bid response, the SSP evaluates, and the higher bid, the DSP that is willing to pay more for the space will win, receiving a win response, and the advertisement will place the ad in that space, generating what we call an impression or a show. So in our case, or we are on the demand side, we have a DSP that is continually receiving traffic from the SSP. We are receiving a huge amount of traffic. Here you can see from the load balancer we have defined in OWS. In our two cloud, we have one in US East and one in US Central. We are receiving an average of 4 million requests per minute in US East and 2 million requests per minute in US Central. That is an average minimum, is a minimum of 42,000 requests per second that we are receiving. All this traffic must be received, processed, and matched against active campaigns in order to answer back with a bid response in case we are interested. As I said before, all this communication end-to-end will have to happen in less than 150 milliseconds. That allow and force us to really make all this evaluation in real time. And also for all this traffic, we have a big part of this traffic that is of no interest to us, and only a small fraction will match against active campaigns. So we really need to filter this traffic in order to be efficient. Also, we want to maximize the number of wins per bid request, since all of the evaluation of a bid request suppose a computational cost. We need to maximize the revenue, maximizing the rate between the bid response, the number of bids we made, and the number we won and we can monetize. That is the win responses and shows produced. Here we have the real world implementation of the proposed solution, where we have the traffic, where we have the incoming bid request coming from the SSP that is reaching our system, and we have the data ingest and process system that is in charge of filtering the traffic as a front of our cloud. This subsystem will filter the traffic based on in two sets of criteria. On one hand, we have the metrics recollection subsystem that has been fed with all the incoming traffic information, with all the bidding metrics from our DSP, and also for the application service with the campaign configuration. All this information is is stored in the metric subsystems, and we are making a calculus of the demand, which kind of traffic each of the active campaigns we have in our subsystems needs to reach their goals. And with it, this information that is fed back to the metric subsystem, we make a calculus based on incoming traffic or how much traffic of each kind we need to match all the active campaigns need to reach to their goals. This generates the initial filter configuration where as a fraction of the traffic will be let pass. That is matching the needs of the active campaigns. And on the other hand, we are storing the historical information of traffic arriving to our cloud core for bidding. We are storing it in our data lake together with which what has been resolved in a bid request and also in a one response. And with all this historical information, we are executing machine learning processes that generate optimization model. Those optimization models are exposed through optimization API, sorry, and that will be used also in the data ingest and processing subsystem, and that will allow us to also filter out and keep just the traffic that will maximize the probability of our target KPI, that in our case is that a bid response, that bidding for a bid request will result on a one action. So together with all these two filtering processes, the traffic that arrives to our DSP will be the best traffic that will allow us to bid most efficiently with the minimum amount of necessary resources. Each one of those subsystems are managed independently, escalate independently, that allow us to also improve the resource management. So just to show you, as I told you, this is a real world implementation. Is implemented in our architecture and is successfully working. I will show you the different metrics and information regarding the data filtering and processing. In this first wallboard, I will shows the metrics for the data ingest and processing subsystem. Here we have different graphics. We have the processing time graphic that show us the amount of time needed for the average amount of time needed for a request to be evaluated and filtered. Here we see the time is less than 1 millisecond. Is an average of 0.4 for this interval of time. That is in the full time of the 150 millisecond. Is really a minimum overhead added for this improvement. In the request received, we are seeing all the raw traffic that is coming to our cloud and we can see, as I said before, we have is not continuous, it's oscillating, and we have here that we are receiving in global for the region 70,000 requests per second. After applying the filtering rules, we just leave around a third of the traffic. We have passed from 76,000 maximum with just to 18,000 requests per second. This traffic is the one that reaches the DSP, the cloud core, and we will actually be evaluated and bid for. We are bidding around 8% of the incoming request. In the programmatic advertising business, we have been told by different SP that is a really healthy metric because the average is expected to be around 2% bidding over the traffic. So this is a very good measure. And over that bid, we have the actual bid request and bid response that we have won, and we have place of advertisement on the ad space that is around, here we have average of 30%. So these rates, bid request, win bid ratio, tell us how efficiently we are filtering and how efficiently we are maximizing the KPI of our traffic. And here also we have the classification we made to our traffic that will match later the demand of the campaign. We classified the traffic by the country that is coming from, so we can also filter and see the traffic, for instance, that we will be arriving to Spain, the different sources that are arriving. So all this flexibility to see the traffic, to classify the traffic, is what allow us to match later the needs of the application service. We see also if it's in a mobile cell phone or a digital TV, for instance, or it's going to be a banner or a video. This information is showing us how we classify and filter the traffic. Later, we can see how the demand of the application service is done. We made a process that, in base of the actual configuration of each campaign, based on the duration of the campaign, the budget, and for instance, the creative that it has, allow us to make an estimation of how many impressions we have to make per second in order to reach the campaign goals. And here in this graphic, we have the comparison of the expected shows that we expect the campaigns to have a continuous delivery against the actual shows that they are made. Here we are saying global for all countries that are less precise, but if we just focus in one country, for instance, in Spain, how the demand is matching the actual shows, just to see if we are matching the demands of the active campaigns, we see how once we detect that there is lower demand, the traffic decreases, and when there is a higher demand, the actual impression grows with them. So that we are making an accurate calculation of the demand of the campaigns, that so we can adapt our rules to that demands. As I have said before, this is calculated at a campaign level. So we may see here for a single campaign, we have the expected show that target a continuous delivery and how it matches the expected calculation. We have some disturbance here that later it has recovered the delivery. So the calculation matches and we guarantee that the campaign will reach its configured goals. And here we can have a vision of how the filterings, the demand estimation works together to allow for the scaling of the computational resources. Here we have the metrics we have seen before, the expected shows against the current shows, the request filter, how much traffic are we receiving for this kind of traffic from the SSPs, and how much are we filtering and letting pass to the cloud core. So we see how the demand is matching the actual delivery, and how we keep almost a very low, we are just keeping a fraction of all the traffic that is coming. And if we just focus on the expected show and the request filter, regarding this is the computational resources that we have allocated on a cloud core for the bidding, we see how they adapt in time when we have lower and higher traffic. There is another condition to keep like the number of campaigns, but we can see that there is a trend here that depending on the demand, we have less demand, we filter the traffic because there are less demands, and we need less number of instances to handle of the incoming traffic that we are receiving in the cloud core. So we optimize resources and cost. And also talking for the KPI optimization and the application of models here, to be faster to access, it will have one of the demonstration video, where here what we show is we generated a, a model to optimize the the wins for a specific kind of traffic that is for the Mexico, from Mexico, from banners in mobile devices. As we can see here, when we have this metric that is the precision threshold of the model, what is the minimum probability they have to reach to be a valid request. So we see here that it has to be at least a probability around 0.4 over 1. And we see that from all the traffic that it has been previously filtered, only 20% of the traffic is has a higher probability that it will be the traffic that will reach the DSP. And we see that here, from the moment we apply the model, we have a slight increase of the bit of around 10%, but we are like double the number of wins events for almost the same amount of bit. Here we can see it on the win bit ratio where we are passing from an average of 26.7% to an average of 32 win ratio, showing that we have improved the KPIs and we have maximized, we have increased the revenue of our application from the same amount of resources and going back to the previous state once the model has been deactivated. So this shows us how the model was performing. And in this graphic we see what is the overhead of applying optimization model on the bit flow and the in the bit flow, how much overhead is adding. We see here from the first model, from the moment it was activated, here we have the probability as we have seen before, and here we have the times. For both regions, we see that the prediction time when we active, it was less than 0.1 millisecond. So it was only a fraction of a millisecond. So the overhead that adds to the whole process is really irrelevant to the whole process. So with this demo, I finish my presentation. Here we have presented a solution to face the problem of massive data ingestion and processing in high demand services with a proposal of architecture and implementation, and that focus on the traffic pre-processing and filtering in the cloud edge. And we have presented a practical case in programmatic advertising when we have shown that it added no overhead in this pre-filtering comparing to the overall time. We have intelligent resource management. We can see how it has scaling and scale out, allowing to optimize the used computational resources, how the traffic has adapted to the application serving needs, and also how by the application of machine learning, we have optimized the KPI, but selecting the traffic that maximize the probability of reaching that KPI. So that is the end of my presentation. And if you have any question, I would be glad to answer them. Thank you.
So thank you, Victor. Really great and impressive work.
Thank you.
I think it meets by far the goals that we defined for Work Package 2. So thank you for the effort and for the great job you have accomplished. I would like to open the floor if someone has any question. Just raise your hand. If not, I have just a brief comment question related just to the application of the system that you have built into other business areas. Obviously, you have just built a solution that is of general purpose, but just to prove the actual performance of the solution, you have just implemented a version for the business in which TapTap operates. Well, through the following the process of all the work you have done, and just in this presentation, I would like to emphasize the fact that what you have built, it's useful and extensible to be used in other contexts, in other businesses, in which there is a very high demand of request flow. In this case, it's build request, but in other cases could be any other sort of request. So just I would like just to you to comment a bit about this.
Yeah, exactly. Or just to complete what you said, or solution is what it takes from a general implementation. And to be applied for other cases, the only requisite that you have to make is to identify what is the different features of our traffic that matches the need of your application. So the persistent metrics, you can match all of them to generate all the rules that will allow to filter the traffics. The thing that you need to make is just to identify what are the main characteristics of your traffic, how they match your application services, in order to store them and apply them to the data ingest and processing subsystem, and the same thing with the optimization model, which are the features that you want that identify, which is the KPI, adapt them, and you will be able to, for instance, apply to stock market, to social media iteration, if you know what is the content of the message and how to know if it's relevant or not. So you can adapt this for all different cases.
Okay, so yeah, basically, that's you explain it much better than I would do. So thank you, Victor. Again, thank you to Tap for the amazing work you have done to complete the work in Work Package 1. And then we move, I give the floor now to Elastic for Work Package 3. There are several people from Elastic, so I don't know who will take the floor.
Hello, can you hear me?
Yes.
Yes. Okay, thank you. So let me.
Yeah.
Peter,
you maybe need to just stop sharing the slides. So.
Okay. Am I sharing?
No.
No.
Now you are sharing your screen.
Now I'm sharing my screen,
Yeah,
and now
that,
I guess you see my PowerPoint.
Yeah, we see it.
Okay, perfect. So thank you very much. I am George Kalajatonakis from Elastic, and we are going to present this deliverable 3 of the PRITIA-CLOUD project, titled Final Prototype of a Solution for Monitoring and Predicting Cloud Resource Usage Costs. This deliverable updates and complements the previous deliverables, presenting the fundamental requirements, the initial defined architecture, and the proposed detailed design. During the implementation of this final prototype, the overall design of the solution have been remained unchanged. The important features that have been introduced are in advanced time series prediction algorithms, such ARIMA and SARIMA. We will see them later. These have been fully integrated, allowing for projections and predictions of the cloud resource usages, and the system has been also updated, enhanced to get information from more infrastructure, cloud infrastructure. So in addition to public cloud infrastructures, we monitoring and predict capabilities in cloud edge environments. So in this deliverable is the final solution that enables the historical monitoring of cloud resource usage, but also prediction of future usage and costs. There is this demonstration video available at this link. I don't know if I can copy paste. Sorry, go back, go back. Okay, if I can share it in the chat because it is included in the PDF, but in the version I had, the link was not correct. But okay, that's not an issue. I will share it on the chat. So first, to establish the problem by showing an example use case. So what's the idea? You have a cloud-hosted digital service provider, this SaaS provider, that wants to provide services to their customers. In order to do that, they need to acquire resources on the cloud, and each resource may serve one or more services. And these resources cost money in many different ways. And as long as your numbers are small, this is easy to handle. But the more you scale, this becomes much more chaotic. And then you have problems to understand why a certain customer costs more money than some other one, or to spot which customer of yours costs you more money, or which service. And the cloud provider provides the usage and the cost of its service, but they cannot provide this breakdown, the cost breakdown per service and customers. And this is what this solution tries to tackle in a very high level. So this was the architecture from the previous deliverables, and it was kept as is. The implementation was in two phases very quickly. There were three essential modules that were developed: the data collection from public cloud, the basic processing algorithm for allocating resources and costs, and the user interface that has the visualization of historical information. And in parallel, we developed the predictive algorithms, which are fully integrated in this final deliverable. And the second phase, we focus on integrating all these in a generic system to get information from additional uh, cloud infrastructures, the full implementation of the predictive algorithms, and the effective integration of resources located at the cloud, the edge, cloud edge. The components of the application that have been integrated into the final prototype, I have labeled with new the ones that have been added in this deliverable. The data collection is okay. We collect data. With what kind of data we collect? Resource usage and billing information, and also the the usage of the services via the tracking service. The data processing, which also now have time projection capabilities, the visualization and the user experience that have advanced visualization and drill down capabilities. Access control was already there. The user management and the permission control, we added some more user role and distinct permission layers, and the management and tagging of resources. This is in order to group into logical groups the resources and customers for the algorithm to make sense. So these are the functionalities as described in the deliverable. I have highlighted with green the new ones. So in order not to waste time for the presentation, for the support of multiple cloud technologies, we have G-Cloud, AWS, Azure, and then also we included the Cloud Edge computing provided by those, for example, the distributed computing for Google. The monitoring of the resources is real time. The activity indicators are centralized storage. The new is the metrics and statistics import engine for IT infrastructure monitoring. I will explain that in a bit. Um, okay, the metrics import engine for resource usage by service and clients, the flexible resource tagging, those who were already there. The forecast is the new, the ability to parameterize basic cost and consumption projection algorithms. So the application, as we will see, runs out of the box with good enough parameters, but the customer can also touch parameters for the algorithm to change behaviors. The service is scalable, and also the last two can be what is the same essentially. It's the reports and the results. It's the ability to project source users uh, to see the evolution of the resource consumption and to drill down a breakdown by service and by customer. So very quickly, for the metrics and statistics import engine is a central component of the cost monitoring and prediction. It is seamlessly incorporated to get all the statistics into one place. It uses standardized connectors, RESTful APIs provided by the cloud providers. The architecture is designed for scalability and adaptability. So it normalizes the the inputs into one place, so it can be used by many different sources. It is compatible with standard protocols such as Prometheus. It has both batch and stream operation modes. I have talked about normalization already, cross-analysis and correlation of metrics. And this is because we need many different sources of information in order to get to make this cost attribution result. We capture and analyze information of both cloud and the edge for comprehensive performance evaluation, and the identification of potential bottlenecks of inefficiencies that could impact cost and operational efficiency. For the forecast, as I have already stated, okay, we have many statistical algorithms. The example are ARIMA, SARIMA, and LSTM. Anticipate operational budgetary needs in real time. So we had a microservice that gets the data in real time when the user makes some user interface changes and provide the expected value. We'll see that in the video. There is a robust pipeline for data cleansing, information, transformation, and normalization. There is a combination of traditional statistical methods and deep learning techniques. The processing is in real time, and extends application from cloud edge environment to traditional clouds. Yes, because the data are normalized in a similar way. The ability to parameterize the algorithms. Okay, I will say that very quickly because okay, I feel that yeah, okay. The parameterized environment allows for fine tuning for great accuracy and efficiency. It's a user configuration. And the functionalities F11 and F12 is about the user experience and the dynamic reports visualization interface. Identification of usage patterns, potential problem areas requiring attention through consumption visualization, the projection of future resource usage behavior, the evolution of the resource over time, visualization to see segmental reports for granular data analysis. Okay, a breakdown of resource usage and cost by customer and service, and the understanding of current state of the IT infrastructure supports quick identification by seeing the resources, the actual resources you have in the cloud and their consumption. So how does the application work? Essentially, you create a project and connect it to Cloud Monitor API services. This is done by an onboarding wizard that uses an API key provided by the cloud provider. It's different for each one. Once you import your resources, then you configure your customer service and resources, and there is some transient period during which the model is trained. And then the cloud usage and costs are continuously monitored, and the results are continuously updated. So we have this the project view. The project is essentially a collection of resources from a specific cloud provider, such as G-Cloud or Azure, with a different monitoring configuration. A project's role is to bridge specific cloud resources with our different applications and services. So if someone gets inside a project, then they will have this tabular way on see either the customer view, the services view, and the resources view. And they are similar, but with some there are some differences. So we see these are the customers of our customer. Essentially, they are the service consumers. Okay. And so once we are in one of these user or service view, we can drill down into each one and then get a more detailed view on each one. So we get a pie chart for the specific the breakdown per services. We have the total cost, we have the active user timeline. This is updated in real time. And there is also the forecast based on the previous periods, previous billing periods. Each billing period is 1 month by definition. And we can select the billing period here. We see different, the past values, and the forecast gets updated accordingly. So for resource utilization, we see here there is the list of all the resources we have captured and selected to be monitored. These clouded resources we allocated. For the user in the GUI, whether is a cloud edge or a normal cloud resource, this is transparent because it's handled by the cloud provider. For example, for Google, we have adapted underneath in a transparent way the difference in the APIs and configuration. So the approach, the experience, what you see is the same as in the normal resource. So in the resource view, we see the resources we monitor in the cloud. Say we want to see the details in the virtual machine. If you hit the I button, you see this split this resource cost per customer. And to the right, there is a pie chart showing the split of these resources cost per customer. And the CPU utilization. If it was a disk, we will get different. Okay, so a configuration parameters. I have already talked about the onboarding wizard. This is a 5-step process that allows you to select which cloud provider you want to use, and to select the resources you want to monitor, and also define the naming patterns, so you can use wildcards and stuff. The grouping and tagging, I already mentioned, to group into logical groups, resources and customers and services. The traffic source definition is when you know that, for example, a certain resource is used only for very specific customer or specific services, you can define that. So the algorithm will not give an equal weight in the cost attribution. So you can fine tune the uses and the network traffic breakdown. So this way you can say, define how much of the traffic is intranet, internal, or interzone. These are stuff that the customer knows, and they can fine tune in order to get better results. So how I'm on time? Is there in time to show the video? I didn't keep what time I started, but I believe we are somewhere in the middle, right?
Yeah. I didn't take also the time, but don't worry.
Okay, thank you. So so this is the video. Can you see the video?
Yes.
Okay, so this is the project list, and when you drill down, you get to see the customer view. Well, all these customers have been tracked by the service, so you don't define each one customer to put it, but they are coming by the actual traffic usage. The use is based on a tracking script put in the service, and provides information on the customer, not individual customer, but the domain, let's say. So if you have I don't know, Facebook or some other, you don't get the individual names or anything, but you get a generic domain. So you understand that it's from Facebook that this traffic is coming, and for which service, like it is the portal or the some transcoding service or something like that. So if you drill down into the customer, you get the activity of this customer, so you can see whether this customer indeed has a lot of traffic, or there is something else is happening. If they have a lower traffic, but for some reason the consumption starts to rising, then this is something that gives you insights on how to optimize the situation. Also, this list is selectable, so you can further drill and okay, there is not in the video, but if you selected one of these, then you could further drill and see more values there. Okay, the same goes for the services. It's very a similar situation. All these values have come from the tracking script. And then you see again the active users for this for the specific service split by customers, and then again you get the forecast for the next. Here it says the forecast is for the next month, but this can be configurable to get either more. Here it goes only 1 month just for performance reasons. Obviously, it can be configured to get further insights in the future. And then yeah, here is the resource view. And also we get the resource utilization, which for in case of a CPU, this is for a VM, this is CPU. If it was a disk, you would see the read-write operations. For a database, same. Yeah, and if you select the, you get further down for the specific customer per service for this resource. Okay, here we see the parameters I showed you before in the presentation. And I believe only it's the one last thing is the wizard, which we can put here the name of the project, the ID, and the project key, which we acquire from the cloud provider. I skip all this because sometimes it takes time, in order to get back and forth. Here it had acquired the resources in the specific project, and eventually provides the script that the user can add in their service in order to be tracked. So yeah, that was the last of it. So thank you, and any questions? Yes? Cannot hear.
Sorry, I was mute.
Okay.
So
Okay.
I was saying,
Okay. I was scared.
I was talking, but I was mute. Sorry. And I was
Okay.
just saying thank you for your work, guys, from Lastec. You have achieved successfully the goals defined in the work package 2, defining a fantastic solution to measure the cost and use of resources of cloud providers. It's a very useful tool that fits perfectly what was expected from your work. Um, and I would like to just open the floor to see if someone has um, any question. If not, I think like the presentation was pretty clear to me. It's very into the focus of the program, and I wish in the future we see a lot of success from Elastic exploiting this solution. Then if there is no question, and since we are just a bit ahead, we have a bit of delay, I would like to just give the floor to our colleague from NEC, Jaime, So he can just present the work that Nick did for the Work Package 4.
Yes.
I mean,
Hi, let me.
I think I've been missing. I've been missing the Work Packages numbers. So just to clarify, like Tap did the work in Work Package 2, Elastic did the work in Work Package 3, and NEC did the work in Work Package 4. Now, yes, Jaime, I give you the floor.
Yes, let me share the presentation. Can you see my screen?
Yes, we can.
Okay. So hi, I'm Jaime Fuster from NEC. I'm going to show our work on the PRITIA-CLOUD project. The name of our part of the project is Diseño de métodos de Machine Learning as a Service con garantías de privacidad. So first, as a little introduction, NEC is a company based in Tokyo, Japan. We have over 125 years of history with over 100,000 employees worldwide. We provide solutions across many different areas, mainly telecommunications, AI solutions, public solutions, enterprise business solutions. Yeah, we've been rated as one of the world's top 100 most innovative organizations, and we appear in the Fortune 500. Within NEC, well, let me show this one first. NEC has a big global research and development network. We are part of the laboratories in Europe, which are situated in Heidelberg in Germany. There we, our history, we have throughout our history, we have presented more than 1,000 patents. We have 50 plus publications, peer-reviewed publications per year. We've participated in more than 140 European projects. And we have 40 plus university cooperations. Our main research areas are in data science, security, 5G and 6G networks, IoT and AI platforms, and standardization. Yeah, as I said, we are based in Germany, in Heidelberg, although we have also offices in the UK, Spain, and Italy. We have over 110 staff members, mostly researchers from over 25 countries. And yeah, the main technology areas in our lab are analytics, AI, security, network, and system platforms. So without further ado, let me introduce what we've done for PRITIA. So our motivation, okay, so first let's look at the risks of large language models served in machine learning as a service. First, there are high barriers to local deployment. Large models like GPT-4 require expensive hardware and are often closed source, which forces users to rely on remote APIs for access. Like everybody, I'm sure, like most people here have used ChatGPT at least once. So there's an potential exposure of private information when you interact with these platforms. Since you're sending data to third-party servers, there's a risk of it being intercepted by network eavesdroppers, or it even can be misused by the service itself, using your data without your knowledge to train their models, etc. On the right, we have a figure like illustrating a bit this scenario where a communication can be intercepted by an eavesdropper. So yeah, there's a conflict between utility and privacy. Remote models demand plain text inputs, creating tensions between leveraging advanced AI capabilities and protecting sensitive user data. So there's a critical gap in privacy-preserving frameworks because the existing solutions, as I was saying, lack robust mechanisms to safeguard users' confidentiality during the connections. So we need a way to preserve this privacy of the user when it connects and shares information with large language models, because as in the future, we will start, they will be more and more ubiquitous. Privacy and sensitive data of users is should be protected always. So our solution for this, we've developed a privacy-preserving LLM agent that anonymizes user queries to protect privacy when using large language models as a service. Its core functionality is we take a user query, we extract sensitive information using natural language processing and other techniques, and we anonymize this data, which is the data that is, then we create an anonymized query that is shared with a large language model. And when the large language model replies to the query, we de-anonymize that data. All of that is done by an autonomous agent that uses local LLMs for processing of this of this anonymization and de-anonymization actions, and deciding how to proceed depending on the user query. I will go a bit further into how it works. So first, as I said, we take a user query. Our system identifies sensitive entities within the data, within the query. This is mapped to a database where we store all the past and entities that have been used, and we can map a specific email address, for instance, to anonymized one that was used in the past. And then the LLM agent has access to this anonymization, de-anonymization, and this database tools, and can choose what part of the query to anonymize, what parts not, when to do it, whether or not to do it. So when then it can call an external LLM API like ChatGPT or Claude, Anthropic, etc., and de-anonymize and anonymize the queries, giving the user in the end a response from the LLM that hasn't been that has been processed without sensitive information. So this is the basic, also more specific technologies that we've used. I'll go here, maybe it's easier to explain. For the anonymization and de-anonymization, we've used Microsoft Presidio, which is a platform by Microsoft that is used specifically for anonymizing sensitive data in texts and de-anonymizing. We also use Spacey for natural language processing and extracting entities from the texts. For the creation of the agent, we've developed it using LangGraph, which is a framework that facilitates the programming and testing of large language model agents. For the database that I mentioned that stores all the entities and the mappings, we have used MongoDB because of the ease of use. And then everything is orchestrated in containers through Kubernetes. Our application is like a middleware that can be connected to any major LLM API, such as OpenAI, Azure, OpenAI as well, Anthropic, etc. And for the agents decision making and the process, we've used Oyama, which is a technology that allows you to execute local, easily local large language models that are open source. So you don't have to share any specific sensitive data. I don't have a demo video, but here's a screenshot of the application of how it works. So just an example, like you can chat with any LLM just as you would with in ChatGPT, but you can see in the process that, for instance, here this person is saying their name is Carlos Gonzalez and email is carlos@gonzalez.es. The input to the system shows that it has anonymized, it detected the name and email address and anonymized it. Then this is sent to the external LLM, say GPT-4, and so the external system, the only thing that sees is mi nombre es Gilberto Iñiguez, mi dirección de correo electrónico es this one here, etc. So, and then when it's given back to the user, it's again de-anonymized. Here's another example. Well, same concept. And yeah, this is all for us for this presentation. Thank you. If you have any questions.
Okay, so thank you, Jaime. Any questions? No? Okay, so thank you again. Thank you to Jaime and the team of NEC to have addressed a very challenging work package where the topic was a bit more researchy type with this new type of tools of generative AI, which is one of the most demanding apps in cloud environments nowadays, and this type of solution is the one that Jaime presented that will allow to add a layer of security and privacy on top of LLMs is definitely a need in the industry, and I'm really glad that PRITIA as a project was a first contributor into this direction. So thanks Jaime and the team from NEC. And I would like us to move forward with the work package 5, if I'm not wrong. That is the work package led by UC3M. So Miguel, I give you the floor. If you just can share the slide. I share just a a new set of slides, Miguel. If you can use that one.
Yeah, I'm using that.
Okay, so if you can share that, well, like the work package that we are be leading, it's a work package in which our aim, our goal was to develop a set of tools that was meant to audit and monitoring um, performance and activity of cloud providers and the cloud environment. So over the past 2 years, we have built a number of tools that now Miguel is going to browse us through that try to achieve this goal. And we addressed different type of issues, since privacy on cloud-based providers until aspects like energy efficiency or measurement of network connection in the connected cloud edge continuum. So I give the floor to Miguel so he can give us details about these different solutions.
Yeah, thank you. As Ruben said, I'm going to present the work carried out as part of the work package P5 of PRITIA-CLOUD project. Specifically in work package P5, we've focused on designing and building solutions that can assess these risks in automated and not intrusive way in real world large scale settings. So these solutions are based on a mix of active and passive instrumentation techniques, contextual data analysis, and reproducible methodologies. This makes them useful both for research and for regulatory auditing environments. In this presentation, which is divided into parts, privacy and transparency, I will walk you through the 5 solutions developing, the foundation, implementation details, and key result of each one. The first solution we are presenting is F, an innovative system designed to audit how exposed devices are to web fingerprinting techniques. We use a different approach from the usual. Instead of measuring from browser directly, we inject a measurement script into digital ads. Nowadays, many tracking mechanisms operate without the user knowing, and often without needing cookies at all. From the perspective of the PRITIA-CLOUD project, AdF offers a new way to audit privacy risks in real-world settings using a channel as we spread as online advertising, which is already embedded in most websites and apps. It also allows us to measure at scale how exposed devices are to fingerprinting techniques. And this is key if we want to better understand and control the risk in digital services and cloud platforms. The AdF system is made up of 3 modules. First, there's a JavaScript script embedded in the app. The script collects attributes from the browser, the operating system, and the device's hardware. Then, after some pre-processing, all this data is combined to form a unique hash, which represents the device fingerprint. Finally, a model based on XGBoost, trained on real-world data, determines if that fingerprint is unique or not. In other words, is whether the device is vulnerable to tracking. To validate all this, we deployed the system in real ad campaigns that generate over 5.4 million impressions across 3 separate periods over a year and a half. From those campaigns, we collected more than 1.7 million devices fingerprints, each labeled with an advertising ID. That gave us a real ground truth to train and validate the system properly. The results from ADF show that 66% of the desktop devices and 40 of mobile devices can be uniquely identified. The accuracy of our system is over 80 across all environments, including web browsers and mobile apps. What's more, we found that vulnerability depends a lot on the operating system and browser. For instance, Chrome on desktop is more vulnerable than Safari or Firefox, and Android is more vulnerable than iOS. But ADI doesn't stop at just diagnosis. Based on our analysis of the most distinctive attributes, we also developed a solution. It's called SEAL. It's a browser station that blocks only what is necessary without affecting the user browser experience and helps reduce the risk of fingerprinting by 60%. So ADF is a tool that can audit fingerprinting risk from inside the advertising ecosystem. It offers a repeatable framework that can be used in independent audits, regulation, or even in development of browser. And its use can also be extended to mobile environments and future hybrid platform across the cloud edge continuum. The second solution I want to talk about deals with something we all face when we go online, is app profiling. We've built a tool that checks what kind of interest big platforms like Google, Facebook, LinkedIn, or X assign to each user to show them personal ads. The problem is a lot of these interests just don't make sense. Some are too vague, others are weirdly specific, and that affects not only your privacy but also the kind of ads you end up seeing. So created a browser station and control panel. That way, people could see the interests assigned to them and say whether they agreed or not. We asked each person to browse their social media like they normally do, view at least 60 ads, and check at least 200 interests. That gave us good solid data from over 150 people. Here is what we found. Nearly half of the interest didn't match the person at all. So half of what makes up the app profile just is not right. So now it's true that platform often don't use all those interests. I mean, sometimes they filter them. You can even see that when they tell you why they showed you a certain ad, that means they could create smaller, more good profiles if they wanted to. Uh, we also found a serious risk, the so-called niche interests. These are really specific, the kind that only a few dozen or a few hundred people in the whole country might have. Well, with just four of these rare interests, you can identify someone with over 90% certainty. On top of that, we developed an alternative model inspired by Chrome's topics approach. It relies on fewer, broader interests, not 100 like the big platform use, and yet it actually performs better when it comes to matching a person's real interests. So the takeaway is clear: with fewer but more relevant data points, advertising can still work and work better. With this, we saw that it's possible to reduce the number of assigned interests and remove those with audience that are just too small. This improves privacy without sacrificing the ability to target ads effectively. This solution, part of the P5 World package in PRITIA-CLOUD, is one of our privacy auditing tools and has led to paper published in PETS. Now we are switching topics. We are moving into the second part of the PRITIA-CLOUD's World Package PA5, is transparency in today's cloud services. We'll start by talking about digital sustainability. In this area, we have developed three tools. They help audit and improve how environmentally friendly digital products really are. The tools are Carbon Tag for measuring the energy use of static ads, Carbon Tag Video for video ads, and Carbon Path, which does the same but for websites. These tools measure clearly and at scale how much energy a digital asset uses. Whether it's a banner, a video, or a full website, they can estimate its energy carbon footprint. They don't need physical sensor or any extra hardware. So basically, we use a machine learning models trained with real energy data. We collected thousands of energy readings using a tool called Carbon. It tells us how much energy the CPU is using, and at the same time, we collect data from the browser using a small tracking pixel. This gave us useful info like load times, resources usage, or how content is rendered. With all this, we build a strong data set, then we train models that can predict how much energy each piece of content use, and the results are very accurate with a coefficient of determination of 0.8 and some format we reach as high as 0.91. We've put everything into one system using container, and this makes it easy to scale, automate, and adjust depending on the type of the content. Thanks to that, the Carbon tools fit smoothly into the workflows of ad agencies, publisher of digital platform, and they give real insight into how much impact each advert or web page has on the environment. These tools are already up and running, and they are ready to be used in environmental audits, green initiatives, or digital certification processes. Their solid step towards more sustainable advertising and more responsible internet. Now let's move on the next solution in transparency block is our clustering. This tool was created to solve a problem that's very specific but also very common in digital advertising. How can we tell if the traffic in our campaign is real or if being polluted by bots, script, or fake activity? Invalid traffic causes big problem. It messes up the number, wasted money, and makes everything harder to trust. It affects advertisers, but also the platform that run the ads. Our clustering takes a different route. Instead of just looking at basic data like IP addresses or user agents, we look at how the traffic behaves over time. If it has a natural pattern or if there are behaviors that don't fit. We group the traffic based on how it moves over time. And then we cross-check that signs or fraud like blacklisted domains or known bots or strange mismatches in traffic is counted. This helps us spot which groups of traffic seem suspicious. We tested all of this using real data, millions of impressions from all sorts of advertisers and platforms. And what we found is important. In some big campaigns, more than 20% of the traffic fell into low trust groups. There is the thing, most of these strange patterns don't get picked up by the usual filters. So our clustering catch problems that often go unnoticed. It's not just for after the campaign either. It can be used as an early warning system. That means platform can catch odd behavior before it brings the results. Um, from the project side, this has been a real win. We published the method in a peer-reviewed journal, and now we are looking at how they combine this tool with more traditional anti-fraud system. We are also exploring how to plug into DCPs and perform platforms. Uh, let me tell you now about the last solution, also part of the transparency blog for today's cloud services. It's called NPM, and it measures network quality, specifically download speed directly from ads. It does this without the user having to do anything, so no clicks, no permissions, or no public installations. Just loading the page or the app where the ad appears is enough, and the measurement happens automatically. As you know, measuring network speed normally means going to a site like speed test or installing an app or at the very least giving permission. With at NPM, we remove the barrier completely. So we can run large scale passive audit, which gave us a much more realistic picture of how mobile and fixed networks actually perform. We don't have to rely on user being willing to run a speed test. Basically, so we take the video at itself, the one that's going to be sound anyway, and use it to launch control parallel downloads. We download the video or a small part of it, measure how long those downloads take. That give us the real download speed right there in real time. The whole system is optimized to be lightweight. It won't drain the user data, it won't drain the battery, and it won't overload the browser. In fact, for mobile networks, we limit the test speed up to 110 megabit per second. That way it stays useful, but not intrusive. Behind the scene, there is a modular setup. There is JavaScript embedded in that, and backend system that collect the metrics in real time. And to avoid overloading anything, the script only runs once per device. And of course, because we are using the ad infrastructure, which is everywhere, we can collect data from a lot of places that give us a really good picture of how network perform around the world. We've already gathered data in countries like Colombia, Mexico, Spain, South Africa, or Italy. In most of them, we see that mobile network traffic doesn't usually go above 25 megabit per second. Thanks to this data, we can go even further, and we can break things down by country, but also by mobile operator, by operating system, and even by demographic profile. For instance, we can spot differences between mobile providers into the same country, or we can also see patterns linked to the type of phone or operating system people are using. Now, if we compare these to the tools like speed tests or OpenSignal and Perf, at NPM stand out because it doesn't need any user action at all. It's silent, fully scalable, and distributed. It audits network quality from inside the other layer, which, let's face it, is already built into nearly every website and app. Within the PRITIA-CLOUD project, where the cloud platform and digital services rely heavily on connectivity, 8 mpm helps bring transparency. It shows us how good or how poor the connection really is across countries, across devices, and across all types network. And this methodology has already led to a paper published at the ACM web conferences. And that brings us to the end of this journey. Throughout the 5 solutions we've developed as part of the work package P5 of PRITIA-CLOUD from Universidad Carlos III de Madrid. These tools are already validated, full documented, and ready to be reused or integrated into other settings. In fact, they are already having real-world impact in research, in audits, in regulatory work, and even in industry. Here we can see the contribution we have talked before. Also like to take a moment to thank the entire PRITIA-CLOUD consortium, the Ministry of Economic Affairs and Digital Transformation, and the European Union for the support throughout the project. And of course, if anyone wants to more details about any of these solutions, we will be happy to share documentation result or even code when possible. So feel free to reach out, and thank you very much.
Okay, thank you, Miguel, for your presentation. I obviously don't have any question on this part, but if anyone has questions on this part, yes, please, let us know, Miguel or me, and we will be happy to address any question. If there is no questions about the work package 5 and the work done by UC3M, again, in this case, I would like to thanks the team from UC3M for the amazing work they have done. So many of these tools are really, really useful and are a very challenging problem to address. And I'm personally very happy with the work that we have accomplished as part of the work package 5 of PRITIA-CLOUD. And if there is no more questions, I think we can close the session for PRITIA-CLOUD here and move to the session of yes, putting the camera. I move to the session of A2 PRITCOM, and then I will give the floor to Angel to lead the part of the workshop dedicated to A2 PRITCOM. Thank you to everyone for your time and your presentation of the work of PRITIA-CLOUD.